We use the surname. We'll present a list at the end of Chiara's lecture. So, okay, welcome back everyone. So we are now starting a second day with Chiara, the afternoon session, and please, Chiara.
Okay, thank you very much. So first of all, let me just recap from yesterday. So yesterday I told you some features about black hole solutions in antideceptor and their thermodynamics. So we have studied solution, at least I provided you some examples of solution with no-zero temperature, and we have studied their thermodynamics and their phase conditions. So today in this lecture we are all gonna learn about black holes which are extremal. So extremal black holes have zero temperature, so they're stable. Nevertheless, they have a finite non-zero entropy. I'm gonna tell you what are their features and what is the near horizon geometry, which is very different than the near horizon geometry of Schwarzschild solution that we have seen before. Then I will tell you generalities about theories of supergravity. I cannot really survey all supergravity and all supersymmetry because it would be really too much or too long. But in any case, I will give you the salient features, and also I will tell you how to let's say construct a solution that preserves some supersymmetry. And in order to do so, you need to solve particular sets of equations, which are called the Killing-Spinor equations. And they are first order in the bosonic fields, and I will explain you how to solve them. And we are also gonna do so I printed this exercise here. So this is if you wanna do it, is how to compute analytically and how to really construct the Killing-Spinor for a specific simple solution. As I was mentioning before, I will start solving it during the lecture. I will leave some parts for you if you want to do it at home, but I think it will be pretty doable, let's say. And in the second part of the lecture, the one that will be after the break, then I will give you an overview. So I will construct some solutions in the first part, the simple ones, and then I will give you an overview of the various different black hole solutions in ADS4 coming from gauge supergravity. So for the second part, the solution will be just slightly more involved, so I will not go through all the equations and the Killing-Spinor equations. I'm just going to present them and tell you what are their characteristics and how they are relevant for certain features such as the microstate counting. So first of all, let me just explain you extremal black hole solutions first. And so then let's start with a very simple configuration, which is in flat space, first of all, because also in ADS things will change, but most of the other stuff, like the near horizon geometry, will still be the same. So let's start with the solution of the charged black hole, which is the Dyson nostrum. Solution asymptotically flat space. So it's a solution which is characterized by this matrix here. I'm dealing for simplicity with electric Dyson nostrum, but you can also do it with the magnetic, like with the magnetic solution. Where this is the usual area element for the two-sphere. So this solution, so it is a black hole solution. The singularity is located at r equals 0. So that's kind of similar to what we have learned yesterday. And if you remember from yesterday, in order to find the event horizon, we have to solve this. We have to get this work factor here go to 0, or equivalently is the denominator. So the horizon is located at this. The area is just 4 pi r plus squared, and the temperature written in terms of r plus and minus, because we have two roots, is nothing else than r plus minus r minus over 4 pi r plus squared. So, okay, so from here you see it already that, okay, so solving the fact that this, like solving this equals 0, give you a second order equation, of course, whose roots are this one. So there are two roots here. If you want them both to be real, you have to have that this factor here under square root should be bigger than 0. In their case, you need to have this. So this is so-called extremality bound. So when this is saturated, so when m equal to a certain value q, you have that these two roots coincide. And if you want to see this, also the temperature goes to 0. So for an extrema solution is characterized by temperature equals 0. Nevertheless, this area here, 4 pi squared, it's finite. So these are in general like solutions which are, let's say, simple. If you see, like, if you impose this condition here and equals q, also the matrix simplifies quite a bit. Okay, let's I'm just gonna choose the positive charge just for simplicity. So the matrix becomes simplified. Where you see that indeed the matrix develops a double root at r equals q. So the fact that the word factor like can be seen or at least contains a square is symptomatic of the fact that you have an extremal solution.
Two questions. When we have two horizons, like the solutions, does the second law of increasing area apply to only the outer horizon or the inner horizon as well?
Sorry,
The second law of black hole
when you
mechanics.
have two horizons,
yes.
you mean. So when you have two horizons, the first law is defined as the outer horizon. There have been attempts also at formulating thermodynamics of the inner horizon. The thermodynamics law is slightly different. In particular, I know from a paper, for instance, Alejandra Castro, Maria Rodriguez studied the inner mechanics, inner thermodynamics. And the first law, instead of having, you need to define quantities appropriately, so it's also why it's not well defined, but so for the outer horizon, you have the m equals TdS plus phi q. For the inner horizon, there is a minus sign here. So where the temperature is then computed as the surface gravity of the inner horizon. But you have to make sure that you will also define this.
For the second law, the area decreases of the horizon, or
for the
of the inner horizon?
Well, it satisfies this law here.
Second law of black hole mechanics was that the area always increases.
Yes, the second law.
For the outer horizon, what about the area of the inner horizon?
Well, you read it off from here, I think.
So I think that
So if you increase the m and you fix the fix the temperature, then yes, S will decrease.
Another question.
But the normal, let's say that. Let me just mention that the normal thermodynamics, the well-defined one, is defined at the outer horizon. So that's what we will take it as a definition, as our starting point.
Second question. You said the temperature is 0 for the extremal case, so it is stable, but we should still look at the heat capacity, right? If it's negative, it should.
Indeed, yes.
And it is positive in this case?
Yes, because if you see from the graph that I plotted yesterday, it was the branch for which T versus S was reading. Okay, this is just a bit but was really like has positive slope. So this was we are talking about the point close to zero.
The temperature of the inner horizon is positive or negative?
The temperature in general of the inner horizon is positive. I mean, the temperature you get it from the periodicity of the Euclidean time coordinate. Once you rotate to the Euclidean and you take the time coordinate, multiply the surface gravity to be periodic of 2 pi. Then,
but we only have the outside geometry when we do the rotation. When we do the weak rotation, we only have the outside geometry, right?
For that, yes. So there are some subtleties regarding this. But for instance, in the same case where you have, we'll discuss it later, the inner horizon is similar to what you have, for instance, in the Sitter black holes, you have the cosmological horizon, but the law that it satisfies, they are kind of same. So there is a way to describe this, but it's not really in firm ground. All the law of thermodynamics is defined better, well defined at the other horizon. At the inner horizon, there have been attempts.
Yeah, so where study thermodynamics, it involves certain kind of perturbation. So is this like stable with respect to perturbation?
In general, they say that inner horizon. I think.
Like say you will have a null singularity at outer horizon, so there's no inner structure. Sometimes.
I think that
at least for curve, I think.
Yeah, I mean, you have to really study the stability of the inner horizon, and I think that like in general, the inner horizon is not something stable.
So would that be like restrict to some subset if these variations would keep that stable?
Yeah, yes. I mean, yes. I don't precisely know the status how it is. The formulation of the inner horizon mechanics is still very much developing, also because the inner horizon, like it's not stable.
Okay.
But so yes, that's what it is, the status. But furthermore, for our from what we studied yesterday and so on, all the things that we have studied is like regard the outer horizon.
Okay.
Okay, so let's see where we were. So, as I was mentioning here, in the case of an extremal black hole, you have that the Wolf factor contains a square. This is symptomatic of the fact that you will have two coincident roots, and this will be the same also for anti-de Sitter black holes. But so, if we want, now we change coordinates, we want to zoom in into the near horizon geometry to see how the solution looks like. So, we change the coordinates, and we define R. This is rho, and then we go to the scale time. We see that taking psi to 0 zooms in into the near horizon geometry. Basically, the solution that we have is this. Near horizon above is this one. There's a very different form with respect to the one that we had in asymptotically, like for black holes which are non-extremal, for instance, the Schwarzschild solution, which has temperature. So this one is again a sphere of radius q, and this is just ADS2 spacetime. So let me just mention that for Schwarzschild you have only one root, so you can never have two coincident roots. So Schwarzschild solution always have temperature, and since it can never be written in this, you cannot have you can never develop the second root, so you always do not have this for Schwarzschild. But for a charged extremal black hole, you have that the near horizon geometry factorizes into an ADS2 factor, so it's an infinite root, and an S2 factor, which have also the same radius. This will be very important because this is at the root of the principle which is called the attractor mechanism that I will explain later in supergravity. That tells that basically for extremal black holes, scalars are like the value of the scalars at the horizon depends only on the charges of the solution. So their scalars, no matter which value they take at asymptotic infinity, they are attracted at the horizon to a specific value, which depend on the black hole charges. And this is because basically they have to travel, let's say, quote unquote, like an infinite distance, because they really have to reach all the way down the throat, so that they forget about the values that they had at infinity, asymptotically. So the fact that the radius of DDS2 is the same as the radius of S2 is typical of black holes in Minkowski space. In anti-de Sitter for black holes that I will describe later on, we will see that this is not valid anymore. The radius of DS will be different than the radius of DS2. And this will have consequences in terms of black hole thermodynamics. Moreover, let me just mention that for de Sitter black holes, so if you add the cosmological constant, which is positive, you have even wider kind of near horizon geometries. So even there are three different kind of extremal black holes. So for a de Sitter black hole, this is just an aside. We're never gonna do de Sitter black holes, but for de Sitter black holes you have also a cosmological horizon. So a Reiser Nostrom de Sitter black hole can have up to 3 horizons. So the inner, outer horizon, and the cosmological horizon. So for an extremal solution, you can have either of these coincide. So the two inner and outer horizon can coincide. In that case, you have a cold black hole with this new horizon geometry. But also the cosmological horizon can coincide with the outer horizon. In that case, you have a de Sitter 2 geometry times S2. But also all the 3 horizons can coincide. This gives the ultra cold solution. And the new horizon geometry is Minkowski 2 times S2. So this is just an aside, just to say that different things can happen depending on the value of the cosmological constant. We will restrict though to negative cosmological constant in when we call about when we will deal with supergravity. So let me just so as I was mentioning, we like these extremal black holes because they are stable, they do not radiate. We can do computations on them. Plus their entropy is non-zero, and therefore we can since they're stable, we can use the tools at our disposal, for instance, supersymmetry, to make sure that we give a microscopic account of this macroscopic entropy. As a last remark on these extremal black holes, let me mention that we can also use isotropic. We can start solving the Einstein's equation with isotropic coordinate. Where this is just flat Euclidean line element. So written in these coordinates, the Reiser Nostrom solution is obtained, the extremal one is obtained by setting h equals 1 plus q over, let's say, I will tell it, well, let me how to call it, we'll call it R, with also F, its free strength, which is this. So we can write the extremal Reiser Nostrom solution also in these coordinates here. And this corresponds to having a Reiser Nostrom solution. However, to solve the Einstein's equation are solved by this one, by this equation here. So only this condition here, which means that I can add an arbitrary number of centers. So this is like r equals 0 is the horizon of our solution, because we shifted the radial coordinate. However, I can also, you see that Einstein's equation are solved just by this condition here. So I can have the Einstein's equation solved also by this form of the work factor. So this solution is this describes a solution with multiple centers. So multiple black holes, each of them would charge Qi at a coordinate xi. So this is centers with charge Qi at positions xi. So these are the so-called Majumdar-Papapetrou solutions. They are described by this work factor here. You also have to modify this appropriately, but they're full solutions to the Einstein's equation. They describe black holes at multiple locations. They are held in equilibrium by the mutual electromagnetic repulsion and the gravitational interaction. So this is one of the few examples of linearity in the Einstein's equation, meaning that you can add as many centers as you want, and you can displace them as many in the way that you want, and you still have a stable configuration. So this is the just a write it down here. And if I'm not mistaken, it comes even before, for instance, the Kerr-Newman solutions.
What is the singularity of this spacetime?
So this it's a good question. So this one, you see that when x goes to xi, this goes to the horizon of each of the black holes. So this coordinate, the coordinate patch that you get only with this coordinate here, describes just up to the up to the horizon. There was a paper by Hawking and Gibbons, I think, if I can give you the reference, that continues the solution really inside the horizon and shows really where are the singularities and how is the Penrose diagram, and it's kind of complicated and so on, but people constructed that. But yes, with this you just construct, this just describes all the way in the exterior.
Is it obvious why x goes to xi is the horizon?
Well, it is obvious from here you see that from the Reiser Nostrum, if you follow that logic, you have shifted pretty much the horizon. From R goes to Q to R goes to 0.
This has a time-like killing vector, right? So it's a static solution, which is...
It's a static solution, yes. It's very particular. It's a static solution, and it's a static solution. In this case, it's because the centers are held in equilibrium between because having equal the mass, each center has mass equal to its charge, and so in general the electromagnetic repulsion between the centers is equals the gravitation interaction.
And each of the black holes are extremal.
Yes,
in this.
exactly. You have basically that zooming in throughout, zooming in through all, close to all the centers, you have an images.
Even if you have like opposite charge.
Sorry?
Even if you have opposite charge, because that's just the magnitude of the charge. And if you have 1 plus q and minus q.
Okay, I think that.
Or this should be the charge should all take the same sign. Otherwise, by electromagnetism.
Yeah, exactly. I mean, I think that from this point on, we have from that point on, I have included all, I have assumed that charge is positive for simplicity, and then I think that in general, at least for sure, this holds when the charge is positive. When it's negative, I think, I need to think about it, but for sure with charge positive, this holds. We can think about it.
So just to make a map in my mind, so these chart, even though you spoke about gravity only, but I guess this is also typical coordinates that you for brains when you have intersectional brains and you can create this extreme or plus and also, no?
Yes.
So the multicenter is the same multicenter you can construct with multiple brain sources in space-time, right?
Yes.
And the singularity is still the same in AD classification. When you have multicenter black hole, when you put x1 equal to x2, you still have the singularities and so on. It's the same stuff that we can construct in string theory sometimes.
Yes, I mean this you can embed the solutions in string theory yes. And the point is that I wanted to stress is that this solution just describes outside.
Yes. The R is not the same R as the
exactly.
Right?
Yes. Yeah. So this is one of the few examples, as I was mentioning, of linearity in the Ansys equation, and we will see that. We'll see. I think that we will see in the really last lecture that these solutions are there in asymptotically flat space because they're supersymmetry and so on. But constructing them in anti-de Sitter space has been a long-standing challenge. Many people tried, but they failed. And I will tell you what is the status of finding these solutions in anti-de Sitter and other composite black holes on Friday. Basically, this phase, so linearity phase, so the Einstein's equation for black holes in anti-de Sitter, it's not anymore this condition here. Moreover, there is also a physical reason why these solutions might not exist in anti-de Sitter, is that in general, being in anti-de Sitter involves having another term in the gravitational potential, which is the term u to the cosmological constant, that might spoil the linearity, for sure spoils the linearity condition, but you need to rearrange the value of the mass and the charge to be able to compensate for the cosmological constant. And finding a back reactive solution to the equations with negative cosmological constant so far has not been at least for multiple center black holes. There have been some attempts, but so far no full success yet.
X-size are the locations of the centers of the horizon?
Sorry?
Did you say that X-size are the location of the horizons? Or
The locations of the horizons, yes.
Right.
For each of the horizons. So let's put it this way. So let me just let's see what. So now I did a review about extremal black holes, and now I just want to talk a bit about supersymmetry. So supersymmetry, why we study supergravity and why we want to study these solutions in theories of supergravity. Well, because in general, like we want, first of all, even when we study microstate counting, we can actually compute the microstate. We can derive a macroscopic interpretation only in presence of supersymmetry, because supersymmetry allows us, gives us computational control. So, for instance, in the dual field theory, you can count the number of ground states in the dual field theory. So, in the case of anti-de Sitter black holes, you have a dual boundary description, which is given in terms of if you have ADS4 black holes, you have a description in terms of three-dimensional superconformal Chern-Simons theory, which is called ABGM. But so the boundary field theory in 3 dimensions, you can use supersymmetry, in particular techniques of supersymmetric localization, to count ground states of this theory at temperature equals 0, therefore reproducing the entropy of a supersymmetry black hole in 4-dimensional anti-de Sitter space. But you need to supersymmetry for that. So you need to study these solutions in theories of supergravity with an ADS4 vacuum, which is something that we're gonna explain. So first of all, I don't know how much are you familiar with supersymmetry. Some of you yes, some other not. But okay, so I cannot really tell you everything about supersymmetry now, but I think if you're not familiar, a good, the first review that I read about this was like a supersymmetry primer by Martin. This is a very basic review about the initial, at least about that's a very good introduction, I think, about features of supersymmetry. It's mostly geared towards phenomenologists, so maybe not really for us, but at least the introduction, I think, is self-contained, and it is very nice. So in general, supersymmetry, I'm gonna give you really what it is in a nutshell, and then I'm gonna tell you more about supergravity. So in general, supersymmetry is a symmetry that relates bosons and fermions. So you have the supersymmetry operator Q and a fermion. It transforms into a boson, and vice versa. So in general, single particle states of supersymmetric theories fall into irreducible representation of the supersymmetry algebra. So in general, in supersymmetric theories, matter comes into supermultiplets, comes into packages, supermultiplet, and each supermultiplet has bosons and fermions. Okay. The bosonic, the number of the bosonic degrees of freedom is equal to the number of fermionic degrees of freedom. And indeed, you have, for instance, particles like fermions and their superpartners, and vice versa. And this is really the fact that you have equal number of fermionic and bosonic degrees of freedom is responsible for the fact that you have cancellations. For instance, when you compute loops, the loops due to the fermions, they cancel, they have a different sign that the loops due to the bosons, therefore they cancel each other, ensuring non-renormalizability properties of your theory. So supergravity indeed is a theory that indeed incorporates supersymmetry in general relativity. So you will have a theory which indeed is obtained by promoting supersymmetry to a local symmetry. And you have indeed in theories of gravity, you have the graviton, and supergravity entails the existence of the superpartner of the graviton, which is the gravitino, which is also indeed the gauge field of this local invariance, and it's a particle of spin 3/2. And to base the Rarita-Schwinger equation, for some of you that you know. But okay, so let me just mention that supergravity indeed arises as a low energy effective action for superstring theories. In particular, the models that we are gonna deal with, there will be theories of gauge supergravity in 4 dimensions, will arise as truncation on, so our model will be theories of n equals 2, gauge supra, and we explain also what gauge means. N equals 2 gauge supergravity means that you have two supercharge operators, each one has 4 components, so in total 8 supercharges, and it comes from truncation of a theory or 11-dimensional supra on different 7-dimensional manifolds, which these manifolds are called Sasaki-Einstein manifolds. They are particular, they have particular geometrical properties in such a way that, like if you reduce this 11-dimensional supergravity on these manifolds, you have a theory which in 4 dimensions is supergravity. And many of the models, in particular, the Sasaki-Einstein manifold will be the 7th sphere. So you might have been familiar probably with the fact that you have holography that relates like superstring theory on ADS 5 times S5 and n equals 4 supergametes. With a similar example, you have a like ADS like M theory on ADS 4 times S7, which is equal to a 3-dimensional AGM theory.
So for keeping n equals to 2, I think you made to take the Sasaki-Einstein manifold that actually preserve n equals to 2 because I mean in general I expect
yes.
to break the.
Of course. So depends. Yeah. Okay. I swept under the rug a lot of details here. So indeed, for S7, so if you reduce, well, if you have a background from 11-dimensional supergravity, which is S4 times S7, you actually have more supersymmetry. You have n equals 8, but then we further truncate it to n equals 2 because we want a subsector.
Right.
While if you reduce it on this different Sasaki-Einstein manifold, they are usually regular manifold because it's manifold that they might have different shape, they might have some non-contractible cycles and so on. And if you reduce it on this, you usually have vacuum with n equals 2 gauge supergravity. So we just reduce, like we consider n equals 2 gauge supra, so then it's the subsector common to them. So okay, let me just see how are we doing. So as I was mentioning, so we have a theory. Let me just first this. So we want to construct supersymmetric solutions, and in order to do so, so these supergravity theories, as I was mentioning, we have also like since matter comes into supermultiplets, we're going to have different kind of matter fields. In particular, we will have scalar fields, vector fields, and also like fermionic fields. And in general, what we want to do is that to preserve so we have to solve the Anson's equation, so that come from the Lagrangian of supergravity. This gives a solution to the equation of motion. However, in order to preserve supersymmetry, you have to also impose that the supersymmetry variation of the fields, collectively denoted by phi, they are equal to 0. And since, in general, for our black hole solutions, we work with purely bosonic configurations, so since the delta of fermions is proportional to bosons, and delta of bosons fermions. In this case, we set the fermions, so in order to simplify the problem, what we do is that we consider only bosonic configurations. Therefore, this is automatically satisfied. We have to, in order to find the supersymmetric solution, we have to set this to 0. So this is like, I'm going to say it's a function of bosons. This is a function of fermions. So if we set the fermions to 0, this is automatically 0. The Killing-Spinor equation that we want to get then is obtained by setting the supersymmetry variation of the fermions to be 0. And this will turn out, it will materialize in the fact that we're going to have some equations, first-order equations for the bosons to be satisfied.
Sorry, so we're going to have only bosonic fields or?
For now, so the full supergravity Lagrangian has bosons and fermions because it's invariant under supersymmetry. So so you have to plug in this into the Lagrangian and the action, and then see that the action is invariant up to the derivative. So transform one to each other. However, to find solutions, you can also consider solution just with the bosons and with the fermions to be 0. Because then in that case, the fermions are not there. The fermions are 0, but they drive the dynamics in a way that their supersymmetry variation tells you, like, let's say, implies some equations for the bosons that you need to satisfy.
But they're 0, so okay. But when you transform with this,
Exactly.
so
So
just
their variation is function of the boson fields. So I will show you how supersymmetry variation looks like, so that you can really see how this. So okay, in general, so it means that you have to satisfy some equations for your bosonic fields. This means that also your black hole solution will have some constraints. So this will materialize in some constraints between the charges and the quantities that appear in your black hole solution.
the first equation you wrote is imposing that the on-shell solutions are also pseudo-invariant.
Sorry, which one, sorry?
The first equation you wrote there.
This.
Yeah.
This is just collectively, this I just, like phi, I just collectively,
solution or?
sorry, phi I just collectively denoted with all the fields in your solution.
Why do all the fields have to be invariant?
Because then you have a supersymmetry configuration. Supersymmetry configuration.
So we're imposing this on the solution that we're considering.
Yes.
Okay.
In the end. So usually it happens that that if you solve the supersymmetry equation, so for a black hole solution under specific assumption, if you solve the supersymmetry equations and the Maxwell's equation, then you automatically have a solution to the full Einstein's equation. That is very nice because you can trade solving second order differential equation coming from the Einstein's equation with first order ones. That's usually what happens in these sort of systems. Otherwise, you can just start with a solution as we do here. Start from a solution which solves the Einstein's equation and constrains the parameters that appear inside. That's what you do usually when you don't have scalars and when you already know that the solution is are variant of are fall into the class of the ADS Rice and Nostrum. But okay, so in general, for asymptotically flat, like for asymptotically flat Rice and Nostrum solution, the BPS bound is exactly equal to this. So saturating the BPS bound for the solution to preserve some supersymmetry, you just need to impose this, which is exactly the or the one that I erased there, but it's exactly the condition for your solution to be extremal. So in that case, the two BPS bound and extremality bound they coincide, but this would not be the case in anti-de Sitter space. Moreover, we're going to have two different kind of BPS bounds for black holes in anti-de Sitter. But okay, let me okay, maybe I can just write it here. Start then, I'm going to give you an example of supersymmetry, like a supergravity theory in 4D, and then we're going to solve this equation here, which will be solving the Killing-Spinor equations. So, let's see. So we'll be talking about solutions of the following Lagrangian. might have recognized the Lagrangian from the Lagrangian of the action that I also have written yesterday. This is pretty much the same Lagrangian. I just, like here it said f mu, I put mn. These are just the indices that go from 1 to 4, just to adapt my notation with respect to the notation that I use in the exercises, because it's taken by a paper by Romas. So basically, this is the bosonic part of the supergravity Lagrangian. So this will be supplemented by fermions. But for our purposes, we set them to 0. So in this case, we have a theory of n equals to gravity. So the content in this case, like the supermultiplet, is so this is the minimal content for a theory that contains the graviton. So the graviton is spin 2 gravitini. So it's spin half. We assemble them into a unique field which is complex. And also we have the gravity. Which is just a gauge field. Spin 1, it's a vector field. So this is just the content of the n equals to supermultiplet, n equals to gravity multiplet. You see that each supercharge raises the spin by 1/2. So if you start, or lowers, depending on how you do it. So you start from 2. If you raise twice, you get first the gravitino, you get actually 2 and 1 graviphoton. This is the macro content of your theory. The only spinner that you have in your theory are the gravitini, which we assemble into just one gravitino, so it will be just one field. So in order to solve the Klein spinor equation, we have to set the supersymmetry variation of the gravitino to 0. And I'm going to write here what is the supersymmetry variation of the gravitino. So this I'm just going to denote, just in order to have the same notation of the exercises. I put here, like I define what is the supercovariant derivative as this form here. So this is supersymmetry variation of the gravitino. So in order the gravitino, its supersymmetry variation is basically a supercovariant derivative acting on the parameter, supersymmetry parameter. This is a spinor, which is at this time is undetermined. Just a spinor. So this is the derivative part. This is the spin connection. I don't know if you're familiar with the formalism of the field lines. Maybe you are, I guess. And this is just the gauge fields, gamma matrices, and also the other term related to the, which contains the field lines. So this is, the Lagrangian, the full supergravity Lagrangian, including fermions and so on, is invariant. Well, I mean, the action, let's say, provided that you plug in this supersymmetry variation of the fermions plus the supersymmetry variation of the bosons. which you can find in the paper by Romas, but I'm not going to write down, the full action is invariant up to a total derivative. It's not fun to show. I did it in my first year of PhD, but you can really show it. Therefore, you have a supersymmetric theory. So now we are going to try to solve this equation here, and we're going to see what this equation tells about supersymmetric, like in which way the requirement of having this supersymmetry variation of the fermions to be 0 constrains the value in our Black solution.
Sorry, I thought we were going to set the fermionic fields to 0, but not the variation.
So in order, for the moment, no, we're going to set the supersymmetry, so we're going to set the fermions to 0. If we want a supersymmetric solution, we want the supersymmetry variation, both of the bosons and the fermions to be 0.
Yeah.
The supersymmetry variations of the bosons, they are proportional to, like, the function of the fermions. So they are automatically 0 once you impose that the fermions are 0.
Yeah, I think I finally understood what you're saying.
So the only one that we need to check, they are the supersymmetry of the fermions, which will correspond to equations for the bosons. Is that clear? Otherwise I can also tell again. So basically we are just, so we start with a theory which is invariant under supersymmetry, but the solutions that we found to this theory might break supersymmetry. So we need to check that the field configuration is supersymmetry by itself, and we do this by checking that this equation is satisfied on the solution. I still didn't specify what are the solutions, but the solutions are a solution to the equation of motion of that Lagrangian there, which we have already seen yesterday. So let's say black hole solutions of the Nernst equation. So these are written down the simple solution to the Nernst equation, which are the ones that we did that we have dealt with yesterday.
Are you also considering interactions between the photon and the gravitino, for example?
The what, sorry?
The graviphoton and
Exactly.
the gravitino, are they interacting somehow?
Yes, but I mean, the point is that, I mean, they interact, meaning they will be terms that couple fermions and their stuff in the fermionic part, that for the moment, like in the Lagrangian, I just set it to 0.
Okay.
But there's no coupling between fermionic and bosonic, right?
Yeah, there is.
This is also through the spin connection, right?
The spin connection is here. Yes.
I mean this contains interaction between, encodes interaction between the fermions and because it can be expressed in terms of the field, right? Which is
Exactly.
the gravity.
So you're gonna have like, so I didn't write down there, for instance, the Rarita-Schwinger equation
Yeah.
for the gravitino.
and also the derivative in the related finger part, will it be a case if you want your derivative with respect to the photon as well?
Exactly, yes. That's what
Okay.
you get. As
And the whole Lagrangian, even the interactive parts are invariant?
all of them, yes. I checked explicitly during my first year of PhD.
Okay.
So yes, you can. So I'm not writing the full Lagrangian. We will not need it, the full Lagrangian with all the fermions. But trust me, they are all invariant once you write the term, like the term correctly. And it is gauge supergravity, meaning that like I didn't explain it here because I wanted to be a bit, just a few details, but it's gauged in the sense that the solvable property are symmetry is gauged, and the field responsible for it is the graviphoton.
Which field?
Graviphoton.
Okay.
You have only one gauge field in the game here at least, so that's what you get.
And well, and the gravity.
If you, I mean, spin one.
Okay, I mean also, and the gravitino is the gauge. It is the gauge field of local supersymmetry.
Exactly. Yes, but it's too hard. So it's too
Oh,
hard. Right?
okay.
Yes. So I mean, only the graviphoton is the only spin one field that you have. But so just to be clear, we have a theory which preserves some whose action is invariant under supersymmetry. We are gonna find solutions. In this case, we already know that the solution to the bosonic Lagrangian, they are the ADS Meister-Nordström solutions. So they're very simple. They're here. To this entire thing, we are gonna require the fact that delta psi m is equal to 0. Because in this case, we're gonna have that the supersymmetry variations on the solutions are 0. This means that we will find some constraints between all the parameters that are inside the solution. And I'm gonna show you why or how. Okay, maybe I'm gonna do something like this. I'm gonna explain you the different, since I have 5 minutes, I can explain the two different kind of supersymmetric solutions. And after the break, either I'm gonna try to solve some of the points in the exercise, or I'm gonna give this as an exercise, and then we can do it, and then we can discuss it during discussion. But okay, so upshot of this, imposing this solution, this equation here, will give rise to the Killing-Skinner equation. Which are actually 4 equations, one for each component, because this is a space-time index. This goes from 1 to 4 or from 0 to 3. So you will have 4 equations, as you can see it in the exercises. And the fact that you impose this will constrain parameters in this way. So we're going to have two kinds of supersymmetric solutions. So we also call it supersymmetric, or we're going to call it also BPS. Okay, they are synonyms. So the first one is the electric Meister-Nordström ADS solution. So for this solution, the magnetic charge is to 0. So I have included both, like the solution, this is the ionic Meister-Nordström solution, meaning that the gauge field has both an electric component and also magnetic components. I denoted with Q the electric charge and with H the magnetic charge. So for the first electric Meister-Nordström ADS4 solution, we are going to have these constraints between the charges. So in order to find a solution to this equation here, this is one of the cases where you can find a solution. And so, in this sense, this is one solution which really resembles the asymptotically flat case. However, if you plug in these parameters inside that equation there, inside the work factor, you will see that this is a naked singularity. However, if you send the limit g to 0, sending g to 0 is like sending the cosmological constant to 0. I call it g because it's the gauging parameter, but its inverse is the ADS radius. So this is the first case. So the first case has an asymptotically flat limit, however it gives you a naked singularity. The second case in which we find a solution is the cosmic so-called cosmic dion. That's how the first author of the paper that has found it is Larry Romans, called them cosmic dions. For this solution, the mass is equal to 0. We have a precise value of the magnetic charge. The magnetic charge is equal to 1 over 2g, and Q is unconstrained. These solutions are again a naked singularity. However, flat unit so these are two different kind of solutions. I don't know if you can see it from here. But basically for one, the magnetic charge is set to 0. This is actually a 1/2 BPS solution, so it preserves half of the supersymmetry. For the second solution, instead, we have the magnetic charge is fixed to a specific value, and this will be something like a characteristic of all the solutions which preserve supersymmetry in this way. This way of preserving supersymmetry is also called topological twist, because basically, as I wanted to see in the exercise, some components of the spin connection are cancelled by the gauge field. So if you see from here, sending the G to 0 is not a well-defined limit. So these solutions here are 1/4 BPS, and they exist only in this sort of theories with ADS vacuum. These solutions here, they do not have any counterpart in asymptotically flat black holes. Also, for these sort of solutions, they are important because once you turn on scalar fields, this will acquire a horizon of finite size. So this will be the solutions which preserve supersymmetry that people have used for the microscope quantum. For this sort of solution here, instead, you cannot shield the singularity even if you turn on scalars. So in this case, by maintaining a static solution, you will not be able to have a horizon. In order for this solution to have a horizon, you need to add angular momentum. And this is something that I will come back to at the end of my lecture.
So is it like the naked singularity in the sense of the D1, D5 black hole, kind of a small black hole?
Yes, exactly.
Same.
Yes.
So it's basically the analysis. So if you put momentum on, you have a microscopic three-charge object.
Yeah, I mean.
But this becomes 1/4 BPS, I guess, no? But if you turn on some momentum,
Exactly, yes. So by turning on angular momentum, you have a 1/4 BPS solution. In that case, you can also just have a solution with the one charge, and so you only have a solution with Q and J.
Okay.
And would be, if you want an extremal solution, there will also be a relation between them.
I see.
I will discuss the number of parameters that
Okay.
we depend on later. But so okay, in my exercise, that probably I can try to do it later, just very briefly. I will tell you how to get this solution here from the King spinor equation. We'll see how the various terms, they just conspire themselves if you impose this condition here in such a way that you get a 1/4 BPS spinor, which means that you have an epsilon parameter with just 2 out of 8